Welcome to The Explainer. Today, we're digging into what might be the single most important invention in our planet's history. It's a tiny, biochemical machine that literally terraformed our world. And the whole story started when a single microbe kind of stumbled upon a solution to what seemed like an impossible problem.
So, if I ask you where the air we breathe comes from, you'd probably say photosynthesis. And you'd be right. But the story of how life actually learned to make oxygen, well, that is anything but simple. It's an evolutionary epic that's been unfolding for 3 billion years, full of trial and error, and one absolutely brilliant breakthrough that changed literally everything. And just to get a sense of the scale we're talking about, look at this number, 130 terawatts. That's the average amount of energy captured by photosynthesis across the entire globe. To put that in perspective, that is about 8 times the total power consumption of our entire human civilization. This isn't just some biological process, it's the most powerful energy engine on the planet, by far. Right, so that engine is the foundation for pretty much all complex life on Earth. But here's the twist. The version we all know and love, the one that takes sunlight, water, and CO2, and gives us sugar and the oxygen we're breathing right now, that wasn't the original model. Yep, you heard that right. It's a sequel. For more than 1 billion years, life had a totally different, you could say more primitive, way of harnessing the sun. And understanding that original version is the key to appreciating just how revolutionary the upgrade was. An upgrade that, made our entire world possible. So let's imagine an early Earth, an alien planet with basically no oxygen in the atmosphere. The main type of photosynthesis back then was a process we now call anoxygenic, which literally just means no oxygen produced. It was clever, for sure, but it had some serious limits. Okay, this chart really shows the fundamental shift. The original version, the anoxygenic one, used stuff like hydrogen sulfide as its fuel source. And it worked, it did the job. But its byproduct was solid sulfur, and it relied on just one pretty simple photosystem. Now the sequel, oxygenic photosynthesis, made a critical switch. It started using water. And this was the game changer. Water is absolutely everywhere, but cracking it open required evolving 2 photosystems, and it produced a byproduct that would completely transform the planet, oxygen. But why was that such a huge deal? Why was switching from hydrogen sulfide to water this massive evolutionary leap? Why did it mean life had to completely re-engineer the whole process? Well, the answer comes down to just how incredibly stable the water molecule is. Splitting water is kind of like trying to crack open a fortress. It does not want to break. Life needed to generate a massive electrical charge to rip electrons away from it, and that original single photosystem machine just wasn't powerful enough. It simply couldn't generate the voltage required. Now, if you want to get scientific, this all comes down to something called redox potential. It's basically just a measure of how willingly a substance gives up its electrons. Hydrogen sulfide, it gives them up pretty easily. Water, on the other hand, holds onto its electrons with an iron grip. Its redox potential is so high, it makes it one of the toughest molecules in nature to crack. So how in the world did evolution solve this? It invented a biological 2-stage rocket. Seriously, instead of trying to get all the energy it needed in one big go, it figured out how to couple 2 different photosystems, photosystem 2 and photosystem 1, together in a series. The first system gives an initial energy boost, then it passes that electron to the second system for a final, much more powerful kick. And together, they finally generated enough energy to do the impossible, split water. But even with a 2-stage rocket, there was still a piece of the puzzle missing. Life needed a catalyst, a special component that could handle the incredibly intense chemistry of splitting water. And it turns out the key was a humble metal. Its story is really what unlocked this whole new world. For this huge leap to happen, 3 key things were needed. First, a photosystem with a high enough potential. Second, a special bioinorganic catalyst to do the dirty work. And third, a way to link those 2 photosystems together. Now, the 2-stage rocket solved that third problem, but what about the first 2? In what is just a moment of pure evolutionary elegance, the answer wasn't some complex new organic molecule. Nope. It was a simple metal ion that was just floating around in the ancient oceans, manganese. This was the perfect stepping stone, the missing link between the old photosynthesis and the new. And the reason manganese was the only option is just fascinating.
See, the ancestral photosystem, the precursor to our modern photosystem too, had evolved in a way that its physical structure literally blocked other electron carriers from getting close. It essentially built a wall around itself. But that wall had a tiny little door, one that was perfectly sized for a small ion like manganese. Evolution had basically backed itself into a corner where only manganese would fit through the door.
So here's how scientists think it all worked. The photosystem would get hit by sunlight and use that energy to strip one electron from a little cluster of manganese ions. Then a second hit of light would come in and remove a second electron, then a third, and then a fourth. With each step, that manganese cluster built up a more and more powerful positive charge. After 4 hits of light, this cluster had enough oxidizing power to finally attack 2 water molecules, ripping their electrons away and releasing a single molecule of oxygen. It was a 4-step charging cycle that basically stored up sunlight to finally conquer water.
The consequences of this one microscopic innovation were, and I mean this literally, planetary. When a single group of bacteria, the cyanobacteria, invented this new oxygenic photosynthesis, they didn't just find a new source of food. They kicked off the single greatest atmospheric transformation in the history of Earth. This timeline just puts the whole epic story into perspective. Anoxygenic photosynthesis shows up around 3.5 billion years ago. Then, about 3 billion years ago, that manganese oxidizing precursor evolves. By 2.7 billion years ago, true oxygenic photosynthesis is born. And then, a few hundred million years later, the Great Oxidation Event begins. This new waste gas, oxygen, starts to fill the oceans and the atmosphere, paving the way for all the complex oxygen-breathing life to finally evolve.
So when you really think about it, the air we breathe, the energy that powers our own bodies, the incredible complexity of the entire biosphere, it all traces back to this single evolutionary accident. A microbe used a biological rocket and a simple metal catalyst to crack open water. And in that moment, what was once a toxic waste product became the breath of life.
And that just has to leave you with a fascinating thought. If life could invent something so profoundly complex and powerful once, what else is out there? As we dig deeper and deeper into the microbial world with things like genomic studies, we're constantly finding bizarre new metabolisms. Which makes you wonder, right? Is this the final chapter in the story of photosynthesis, or is it just the one we happen to be living in?